Correct. All right. Hi, everybody. My name is Ken. Kenneth Kent, but everybody just calls me Ken. I'm here to give a talk, array bytecode support in MicroJIT, which was conducted with our team, Shubham Verma, who's a master's student looking at finishing very shortly. In fact, I should be reading his thesis before I get home. Harpreet Kaur, who's the PhD student who's working on the larger part of the project, and Marius, Pirvu, our partner at IBM. So I'll try my best to do Shubham proud. So the obligatory second slide of the outline of the talk, I'll give you some background on the problem, some of the technologies that we're working around. Since it's with IBM, then we're using TRJIT and OpenJ9, which some of you might be familiar with. We'll talk about MicroJIT and how it fits in, some of the motivation for the work in supporting the arrays, design and implementation, followed by some evaluation and discussion, and then the future work and conclusions. So on the background side, as we all know, just-in-time compilations in JVMs allow us to enhance the performance by compiling it on the fly, and it merges the benefits of effectively having the interpretation and the dynamics and the compilation just when we need it. What we do know about JITs, however, is that one JIT doesn't actually solve all problems. Depending upon your application and the instance, different JIT techniques and approaches work best. So with multiple JITs, the aim is to minimize the overhead and enhance the JVM efficiency. And what we're looking at here is recognizing that one JIT doesn't solve all. OpenJ9 uses Eclipse uses the Testarossa JIT, and it's a great JIT, but it does have its fallacies, as we'll see. So the Eclipse OpenJ9, it's IBM's contribution. It was originally J9, and it was delivered by IBM, and then it was flipped over into Eclipse Foundation, and it was split into two pieces, OMR, which is the underlying base, and then OpenJ9, which sits on top of it and sucks it in. Overall, OpenJ9 was designed for quick startup, low overhead, and high throughput. That was what it was designed for at the start. Arguably, it's digressed or changed in various ways since then. The compilation process checks for precompiled methods, and it uses the interpreter or JIT based on the invocation, and it tries to balance speed and resource optimization. The JIT that's actually used within OpenJ9 is the Testarossa JIT, and that's the default, and it uses selective compilation amongst other optimizations to try and bleed out as much performance as it can. So one of the things it does is it goes from cold to scorching. So as the application's running, it's collecting profile information, and as it hits various thresholds, it then does yet another compilation to try and bleed out some more performance. In addition to that, it employs the shared class cache to try and tuck away any information from previous runs and use that information to kind of get ahead of itself in terms of ideas about profiling. And then it also uses some ahead of time compilation. So when we're talking about arrays within OpenJ9, we need to be aware about how they're actually implemented. And within OpenJ9 itself, it uses multiple GC policies. Two of note in particular are balanced and metronome. These are region-based garbage collection policies, which effectively means it divides up the heap into regions, and these regions can be scattered throughout or reordered, things of that nature. When you're storing arrays, effectively large arrays means that it's going to be stored across multiple regions, and this causes problems because the regions may not necessarily be one after another or contiguous. So the way in which this is dealt with within OpenJ9 is the idea of using a spine, which effectively is a tree-based structure, keeps the head of the array, and then pointers off of that to regions. Each region contains an arrayoid, and an arrayoid is simply a chunk of the array itself. So you can actually split up the array across multiple heap regions. And at the end of it, we have a chain of leaves, which effectively holds the remaining pieces that don't fill an arrayoid or can be jammed in with the object itself. In order to try and improve the performance, with some of the JNI calls and things of that nature where it's expecting contiguous arrays to be accessible. It employs a double map, which effectively utilizes some of the operating system's virtual memory space to actually remap those regions back into a contiguous manner. Okay. So arrays are not contiguous, short order of it. So TRJIT and MicroJIT and OpenJ9. MicroJIT we previously presented at another conference. It's a lightweight, non-optimized code compiler for fast startup, and the way in which it works is essentially just template-based compilation. So for each of the bytecodes, it maintains a template. If it recognizes that a method can be, all of the bytecodes within it can be templated, then it will do so, compile the method, and then it invokes the compiled method instead of the interpreted one. The nice thing about this is that it's very fast in terms of compilation. There's no optimization, just a straight templating, and it can be used alongside of TRJIT. So with it enabled, it gives us quick compilation, and it's much less optimized than TRJIT. TRJIT's delayed, and it gives us a more optimized compilation later on. And so effectively, if we use them together, the idea would be that MicroJIT would have a lower threshold. It would kick in earlier. It would perform the compilation. We'd run with the templated compilation method for a while. Once we hit a higher threshold, then we would flip over to TRJIT and then start recognizing that the method deserves more optimized compilation. Did I go forward? I did, yep. So the MicroJIT performance in general, it's faster than the interpreter. When we benchmark it against the interpreter directly, it is faster. Its efficiency is enhanced by supporting more bytecodes. Effectively, if a method does not have all of the bytecodes within it supported by the templated JIT, then effectively it won't compile the method and it'll mark it as uncompilable by the MicroJIT, and it'll defer it to compilation when it hits the threshold for TRJIT or continue interpreting. What this effectively means is that we need more bytecode support in order to get more MicroJIT compilation. And the reason for this is because the interpreter to MicroJIT switches can be quite costly. So effectively, the more we can MicroJIT, the better the performance we can achieve. So here's a diagram to try and show the control flow. I criticized Shubham about this last night. So the diamond at the top, method already compiled, should mean this method is already TRJIT compiled. Okay, so effectively when a method is invoked, we first see if it's been compiled. It's not hitting a threshold. If we have the compilation of it, we just directly go and execute the compiled code and we're finished with it. If we notice that it hasn't been compiled yet, we decrement the method invocation count. Just a straight counter is all we use for MicroJIT. Once we get to the point that we've hit the count for the MicroJIT, then we'll compile it with the MicroJIT. We'll store that compiled method, and then we'll invoke that. Once we exceed that threshold, but now we start to hit the TRJIT threshold, then we default over to the TRJIT compiler. It'll then compile based upon its first level of profiling, and it'll advance from there with normal TRJIT compilation. Okay. In the event we never hit any of the thresholds, because it's a rarely invoked method, then we always divert back to interpretation. So the motivation for our work is that currently there's no support for array bytecodes, such as newarray, array length, the star aaload, and the star aastore bytecodes. Methods with those array bytecodes effectively switch back to the interpreter. So as soon as we look at them for MicroJIT compilation, we see one of those were there previously. We just effectively mark the method as non-MicroJITable, and then defer it to interpreter until we hit the TRJIT threshold. So by effectively having these bytecodes, now we can, any methods that contain them that was blocking us before, we can now MicroJIT and get that in performance improvement. The compilation phase includes the generation of metadata. It does the pre-prologues, the prologues, and the body generation. So the meta generation phase involves parsing the method signature, mapping the incoming parameters, and allocating the code cache for the method. The pre-prologue generation phase includes instructions to detect if the program stack is getting too full. And then the prologue generation phase includes instructions to save the previous base pointer and certain registers onto the stack. Then it sets the new base and stack pointers for the method. And the body generation is effectively taking the predefined template. That predefined template's written in ASM. And then with that, we copy and patch it from the code generator with the buffered addresses into the code. So here's an example of the aastore bytecode template. You can see here where we grab the values from the operand stack, stick them into the registers R11 and R12. Right? We grab the reference, put it in RAX, then we perform the evaluation, right? And we store the value at the index of the array. The template of the newarray bytecode was a little bit more complex, simply because of the fact that newarray means that we have to do memory allocation, and memory allocation means, well, what's the size of the array? If it's a small array, then we can take the fast path for the contiguous arrays, which effectively allocates the memory in the thread local heap, and it's no problem. If, however, the array is large, then we had to actually deal with that through a helper function. So we had the JIT newarray helper function, which we patched in from outside of the template. We invoke it. It does the allocation for us where it has to create the spline, or the spine, the arrayoids, and any leaves that are necessary. Registers are set up and calculations for each of the primitive data types occur at this point. For our evaluation, we used a basic desktop machine. Okay, here's the specs here from the paper for those of you that are interested. And we measured our time using the log files. The testing and the benchmarking that we used, we developed our own regression testing suite for the MicroJIT. This was effectively based around the idea of testing that each of the bytecodes that we implemented operate correctly and test the corner cases. We don't really use it for performance measurement, just for verification that it actually works and is doing as it should according to the spec. We did use the DaCapo suite for benchmarking and performance, and most of the benchmarks there are running, and we use that to actually try and judge the performance of the system overall. So we evaluated the JVM memory, the compiler performance, and so on. So to give you a little bit of a snapshot of the results, here's a figure where we show the performance of our MicroJIT against itself with arrays and without arrays. So without arrays is the blue line. Effectively, if you run MicroJIT, that's your base case. And then when we turn on the support for with arrays, then we see that in most of the test cases we get a performance improvement. Right? The percentage of time needed to complete is less, with the exception of two benchmarks, Sunflow and Aurora. Here's the specific numbers instead of in a figure, so you can see the differences there. You'll notice the two that we lost performance in was 1.9 and 2.1% respectively. But overall we gained, and we gained by 3.1% on average over the benchmarks. What was more interesting for us, because of the fact that we're trying to push MicroJIT compiling more of the bytecode, was how it actually laid out across the methods and how many more methods we could compile and how many instances of these bytecodes occurred in the benchmarks. So here's a table of the bytecode instructions. On the far axis across the top we have the benchmarks, and along the bottom you'll see the total number of bytecodes that we actually supported additionally by, including the support for arrays. You'll notice that Eclipse was 18,000, but in actual fact, just because you have now support for 18,000 bytecodes doesn't mean that you're actually getting that significantly more compilation. So when we look at the actual benchmarks against the number of methods that we actually have been able to add and compile because of the array support. You'll see Eclipse had a good improvement with 25 more methods, going from 555 to 580 methods we could compile. So that's how many hit the threshold. To trigger MicroJIT, we could do it, and then later on it gets passed on to TRJIT if it hits that range. In comparison to with TRJIT versus MicroJIT by itself, here you can see the benchmarks with the various ones down the top. So the blue is the interpreter only, which clearly has the worst performance. Next is our TRJIT by default. Okay. Next is the TRJIT with cold optimization level. Below that is the TRJIT with no optimization level. And then the bottom one is TRJIT along with MicroJIT, where we have the array support added in for MicroJIT. What's interesting here is that there are benchmarks where TRJIT clearly wins, because it is, once you get running long enough and the methods do get hot enough, that optimization, or that highly optimized compilation occurs, and you actually see the benefit of it because the program runs long enough. However, there are instances where effectively, by having MicroJIT as a wedge in there, it picks up methods, compiles them quickly, gets beyond the interpreter, and then the application terminates before you get to that TRJIT to take advantage of that. So, for example, the Aurora benchmark, which is on the first column, it's 2071 for the TRJIT by default, and when we add in the MicroJIT, we get down to 2049. So we see a slight improvement here with the MicroJIT. Okay, it's not that benchmark. We see it in others as well, such as LuIndex, where we're at 904, where TRJIT's at 945. Okay. So the future work from this, one of them is the adaptive warm-up iteration strategies. So clearly, MicroJIT has its benefit in some applications, but in some other applications it doesn't, because the TRJIT will hit the method, will do the optimized compilation, and it pays off in the long run. So how can we identify where we should do the MicroJIT and where we should not in order to get best performance? We want to expand the array operations support in MicroJIT in general. So we'd like to investigate doing operations like a new array and multi-a new array, which get a little bit more complex. And then as well, the optimization through array bound check elimination. So right now, we have to check the array bounds. If we could eliminate that, that'll effectively give us a little bit more of a performance boost at that point. So in conclusion, the scope of our work, we investigated the performance impact of adding the array bytecode support in the MicroJIT compiler. It did show a benefit, not too surprising. We were expecting to see that. The key findings was that by adding it, reduced the execution time, and handling array bytecode boosts the Java program speed, especially in resource-constrained settings. So we are seeing some memory footprint benefits there as well. The implication is expanding the array bytecode support in MicroJIT. It progresses Java's efficiency in limited resource environments, and it set a solid foundation for implementing more bytecodes in the templated compiler. I'll be happy to answer your questions.
Questions? Please come to the mic.
So what fraction of the Java opcode space does MicroJIT currently cover? And how much further did this push it, and how much is left?
All right, so I'll try to remember the numbers off the top of my head, Matthew.
Ballpark is okay.
I know Shubham would know. So I believe by adding the arrays, we bumped it up by about 10%. We're still missing about, I believe, 20%, right? Some of the key ones that we're missing that's causing us to lose a lot is on the invoke static and invoke special, and those are underway. Okay. And I think with those two, they get us a really good capture, because I think right now we're seeing about 30% of the methods that we can actually compile.
Okay, thanks.
Yeah.
Thanks for the talk. I probably missed the reason why was a couple of benchmarks that slowed down. Do you think that was because like compression overhead increased, or is there any other things you think of?
The reason why we felt those benchmarks slowed down, you're talking right here?
Yes.
Yeah, is because of the fact that the methods that had arrays in them, and we JIT compiled those, we only kind of called them a few times beyond the threshold, and so we didn't run long enough to kind of outweigh the interpretation 3 or 4 more times versus compile it and execute it faster 3 or 4 times.
So it was like just only adding the compilation over here, right?
Yeah.
Okay, thank you.
Yeah. Even as a template compiler, it's going to have that pause, and you're going to consume some more time.
Hello, thank you.
Thanks.
I'd like to ask about whether your code templates for the array bytecodes use vector instructions.
Yes.
Okay.
Don't ask me to give any more details of that, but I know yes is the answer because I know Shubham struggled with them for a while. Yep.
Okay, thanks. Another question, if I may.
Sure.
Does OpenJ9 just have an x86 backend, or does it support RISC-V and other architectures?
I know it does other architectures because it does
Power,
power.
powered, of course,
And it
of course,
also
yes.
does ARM64.
Okay,
Yep.
thanks.
Yep.
Does your JIT only support Intel though, right?
Yes, that was the initial one.
Yeah, okay.
Yeah. Yeah. But there's discussion about ARM64.
Any other questions? Otherwise, we'll thank Ken again for